All right. Hello, welcome to my talk on SEEC, memory, secure, and meets efficiency in secure two-party computation. This is joint work with Nora Kayata and Thomas Schneider, and was part of my master's thesis at Encrypto. And I'm happy that so many of you made it to the last talk of DPMPC. Okay, so some first things for the motivation. In recent years, memory safety of applications and programming languages has received increasing interest, and due to an increasing dependence of our privacy on the security of digital systems, memory safety as one piece of secure systems is becoming more and more important. However, experience has shown time and time again that high-impact vulnerabilities due to memory unsafety are virtually unavoidable in large code bases written in C and C++. And for this, I've brought some data where a recent examination of the high-severity security impacting bugs in Chromium revealed that 70% of them are due to memory unsafety. And this is also corroborated by other big projects, Windows, Android, etc., where they have seen numbers between 60 and 70%. Okay, this is relevant for MPC applications because they are essentially network services potentially exposed to the internet and which are usually written in C and C++. The memory safety of these applications will become more important as MPC progresses from research to real-world deployments. The reason C and C++ are so often used in MPC is because they give us good performance and efficiency of the resulting implementations. Okay, so we also care about efficiency. One part of efficiency is memory efficiency. To shift MPC from the largely theoretical to the practical, we need to optimize its performance and efficiency. That's what we use C and C++. And this is especially relevant if we also at some point want to target mobile devices, which are memory constrained often. For example, the most common RAM configuration was 4 gigabytes in 2022. But it's also important if we run MPC on large servers where being more memory efficient allows us to either tackle larger problems or reduce operating costs. Okay, so what do we contribute with SEEC? Because we wanted to achieve a memory-safe and efficient MPC framework, which also provides good performance and a nice developer experience, the natural choice for us was Rust as a programming language. It's a memory-safe language with performance similar to C and C++, and we have good control of our memory allocations without garbage collection. Also a good developer experience due to fantastic tooling. With SEEC, we provide a high-level embedded domain-specific language which you can use to construct your circuits, and also the option to use fuse circuits or Bristol circuits. We provide a memory and round-efficient implementation of subcircuits, which optionally also support MPC-level single instruction multiple data. Our API supports both function-dependent and independent preprocessing. And what I personally really like is that SEEC is extensible without the need for forking the repository. If you use it as a library, you can write your own protocol and use it with SEEC without changing the source of SEEC itself. And it is also a cross-platform, which we test in our continuous integration pipeline. So, currently, SEEC is aimed at linear secret sharing-based protocols in GMW with semi-honest security and two parties. We plan to extend SEEC to also provide facilities for multiple parties and hopefully at some point maliciously secure protocols. For this, the talk by Peter will be quite helpful, I think. And the currently implemented protocols are GMW with multiplication triples in the Boolean and arithmetic domain, and also a separate protocol implementation where we have arithmetic and binary mix and conversions. We also provide currently partial implementations of ASTA and AVY2 protocols for the Boolean domain. Notably, we've also implemented an oblivious transfer library, which uses the geologically simplest OT ALS set d4s4-3 and silent OT extension protocols. As part of this work, we also developed a benchmarking tool which supports ABY, motion, NP speeds, and SEEC. You can use it to declaratively specify your benchmarks with the varying input sizes, and then it handles all the compilation of the frameworks, the remote execution of the parties or local execution, parsing the results into a common format, and then you can do your analysis on it. Okay, so now on to some implementation details of SEEC, specifically those related to memory efficiency. Here on the left side, we have some simple Rust code with a function that takes 2 booleans and outputs 1 boolean, and is called twice, where the result of the first call is an input into the second call. In traditional programs such as this, we use functions as an important tool for building abstractions and organizing code, but they also reduce the size of the binary. Imagine if we would inline every function of a large program, the result would be an enormous binary. Yet this is exactly what we often do in MPC, in secret sharing-based MPC, which results in huge circuits. Okay, so on the right side, we see what we maybe want secure programs to look like. We want to have some high-level way of specifying a functionality to evaluate securely, and ideally we can declare functions in this high-level way and use them as normal functions without our secure functionality to ease the development of MPC applications. There might be some slight differences, such as change types, but those are okay and likely also necessary. And so with SEEC, we've implemented and extensively benchmarked one possible solution where we can have such functions in secret sharing-based MPC. Okay, so why is that even a challenge? Why are functions in MPC, specifically linear secret sharing-based protocols, which execute in multiple rounds, difficult to achieve? Let's say we have our high-level functionality with 2 function calls, and in this case, those 2 function calls are independent. If we go a level lower and look at the intermediate or in-memory representation in our MPC framework or background, our source code of our secure functionality is compiled and have 2 options. We can either represent the functionality as bytecode for an MPC-specific virtual machine. This is, for example, how MP speeds but also scale number it. Or we can represent the functionality as a circuit or a directed acyclic graph, which more closely resembles the descriptions of protocols you can find in the literature, and is the approach taken by frameworks such as ABY and Motion and others. In the bytecode representation, we have the bytecode for the function once in memory, and then we have 2 sequential call instructions to this function, whereas in the graph-based approach, we repeat the subgraph for this function within the larger circuit for our 2 calls. Okay, so these approaches both have their benefits and drawbacks. With the bytecode executed by the virtual machine, the sequential function calls result in an increased number of communication rounds. However, because the definition of the function itself is only stored once in memory, and we can more easily reuse memory for output of gates or instructions in this case, we have a reduced memory consumption. If we choose the graph-based approach, we naturally get concurrent evaluation of these 2 functions when we iterate over the layers of this circuit. However, this comes at the cost of increased memory, as the sub-circuit for this function is simply repeated within the larger circuit. Okay, so what we've looked at is, can we have memory-efficient functions or sub-circuits which do not increase the number of rounds? And as a side note, this does not apply to garbled circuits, where functions are much easier to support, as there the sequential evaluation of functions does not matter because it executes in constant rounds. Okay, so with SEEC, we provide a memory and relevant efficient way of using the subcircuits in secret sharing-based protocols. And here's an example of our high-level API, where you can annotate a normal Rust function which operates on data of type secret with our subcircuit markup. In this case, the function simply computes the pairwise AND of two input vectors, so a very simple function. Then we can use this function as a normal function in our code. Okay, so for an MPC application developer, this is a nice experience, but how does it work? How can we have this API, but get good memory efficiency and good communication routes? Okay, so in C, we also use a graph-based representation for our functionality to execute. However, in contrast to previous works, repeated calls to a functionality will not inline them for each call. Instead, for the first call to such a function annotated with the subcircuit macro, we build the subgraph corresponding to this function and effectively cache it. Subsequent calls to the function will not recompute the subcircuit, but instead connect the argument gates to the input gates of this subcircuit. For these connections between call circuits, we also optimize the memory required to store them. Specifically, we compress gates with consecutive IDs into ranges of gates. Okay, so the first part is done. We have a memory efficient way of declaring subcircuits, but what about the round complexity? So for an efficient online phase, it is important that using subcircuits does not increase the number of communication routes. In our framework, we achieve this via lazy iteration over the topologically sorted layers for each use of the subcircuit. We refer to this lazy iteration of subcircuit layers as dynamic layers, or DL for short. And the crucial property of this approach is that the execution of each subcircuit is as if it was inlined, meaning we have no increase in the depth of the circuit and there's the round complexity of the overall protocol execution. Also, this graph-based lazy iteration approach enables us to have partial and concurrent evaluation of multiple uses of the same subcircuit or different subcircuits. This notion and our implementation of subcircuits enables us to have memory and round efficient functions for secret sharing based MPC. Okay, so we just saw that with SEEC we can have those efficient subcircuits, but there's also different techniques, namely SIMD, which stands for single instruction multiple data, which have been already used in the past to reduce the memory consumption and increase efficiency of MPC applications or implementations. For example, in the motion framework, we can have SIMD gates which perform the same operation over vectors of values instead of individual values. A nice benefit of these MPC-level SIMD gates is that these gates internally can then use hardware SIMD instructions to achieve a nice speed up and essentially get some computation on gates for free. In SEEC, we also support SIMD, but instead of at the gate level, we support it at the subcircuit level. So instead of an individual gate operating on vectors, we have a whole subcircuit which takes as input vectors of data and produces a vector of data as output. And we do this because supporting SIMD at the gate level can very easily increase the memory consumption of circuits which don't use SIMD. And one of our goals was to support also use cases where you might not operate on vectors of data or have large circuits which only operate on scalar values. Okay, so alongside subcircuits and SIMD, we also implement several optimizations to increase the performance and memory efficiency. The first one of these we call static layers. And layers here refers to those layers of the use of a subcircuit, which, as I mentioned earlier, are dynamically computed in this dynamic layer representation, and this happens in the online phase. So with the static layer representation, we pre-compute these layers of each used as a subcircuit and basically compile one representation into another one. And to not blow up the required memory, we, however, only store the unique layer configurations of each subcircuit. As a result, if two calls to a subcircuit results in the same configuration of internal layers, we only store these once. The benefit of this optimization is twofold. So we have an increased performance in the online phase because we don't need to dynamically compute these layers all the time and effectively do topological sorting. And depending on the circuit topology, we also have a reduced memory consumption because we don't need general graph representation anymore with forward and backward references between gates. The next optimization is early deallocation of SIMD gates, gate outputs. Quite obvious because in SIMD circuits, the outputs of gates are vectors which are heap allocated. We can free them once they are not needed anymore for further gates. And lastly, with our generic APIs for preprocessing, we have the option to pre-compute multiplication triples and store them on the file system. And then in the online phase, we can read the triples on demand in batches from the file. And this reduces the memory consumption as well because we don't need to hold all the required triples for the functionality in memory at once. Okay, so now to the evaluation, and let's see what impact do subcircuits and or optimizations have actually on the memory efficiency. To evaluate this, we've run extensive benchmarks with our dedicated benchmarking tool, which I mentioned in the beginning. We compare with APY, NP speeds, and the motion framework. And in all frameworks, we use the semi-honest two-party Boolean GW protocol with multiplication triples and only benchmark the online phase and the setup. We perform the evaluation in different environments, with differing simulated network settings and a varying number of threads. To measure the maximum memory consumption for each framework, we use HeapTrack as a tool. We ran each party on one of our servers with 32 logical cores and 128 gigs of RAM. So, what functionalities do we benchmark? The first one is effectively AES-CBC, where we repeatedly execute AES-128 change after one another. We chose this functionality as it has this structure of repeated sub-functionality. It cannot exploit SIMD, and the size of the circuit can easily be scaled, and it was straightforward to implement it on the frameworks. And then also, to benchmark our SIMD optimizations, we evaluate ASMCHART256 with different SIMD vector sizes to see the impact of our SIMD-specific optimizations. Okay, so here are the results. First, for the AES-CBC use case for SEEC alone, and note that on this graph and following graphs, both x and y axes are scaled logarithmically. SEEC with the dynamic layers, but without subcircuits, so each AES call being inlined into one big circuit has the highest peak memory consumption of 50 gigabytes at the largest circuit size, which is 10,000 chain IS circuits. If we then use the dynamic layer representation with subcircuits, the memory consumption is already reduced to 2.2 gigabytes. And if we further use our static layer representation, the memory consumption is just 375 megabytes. So this is already roughly a factor of 135 improvement when comparing to SEEC with no subcircuits. So how does this stack up against the other frameworks? Okay, so when we compare the other frameworks, we first see that especially motion has tremendous memory overhead, especially for Boolean circuits not using SIMD, such as this one. Only at 100 chained AES circuits, the peak memory consumption of the online phase is already 73 gigabytes, and we could not evaluate larger sizes because we ran out of RAM. ABY fares better with 74 gigabyte at 10K circuits, but this is still more than the 50 gigabytes of SEEC we saw earlier. For MP speeds and SEEC, the difference is quite small. So while SEEC fares better for very small circuits, with increasing size, the memory consumption of MP speeds is better than SEEC. And one reason for this is that MP speeds low memory consumptions in this benchmark is because we can use loops in the bytecode, which for this circuit don't increase the number of rounds, but significantly reduce the size of the bytecode. Okay, so we confirmed our earlier claims that bytecode representation, for example, used by MP speeds, results in low memory consumption for circuits such as the emulated, whereas the graph-based approach tends to require several orders of memory more. We also see that with our implementation of subcircuits in C, we can achieve memory efficiency that is similar and close to that of the bytecode-based approach. All right, so now let's focus on SIMD subcircuits, SIMD circuits, where we operate on vectors of values instead of individual ones. So here we evaluate the AS128 circuit again with varying SIMD sizes and execute this circuit in parallel and look at the peak memory consumption. For SEEC, we have the highest peak memory consumption of 7.5 gigabyte at 1 million parallel AS cards. For the variant where we only use static layers, but no early deallocation or triple streaming. And this is already improved by using early deallocation of syndicates, and then we further improve it by triple streaming, so we end up at 700 megabytes, which is roughly a 10 times reduction in peak memory consumption. We also see that on the left side of the graph, this variant with streaming triplets requires the most memory. The reason for this is that we read the triplets in batches, and the batch size is quite high in this benchmark. So here on the left side, this high memory consumption is mostly due to essentially loading unneeded multiplication triplets into memory. Okay, so let's again compare with the most efficient variant. The most efficient variant here with the other frameworks. For IBY and MP speeds, we were unable to go up to the largest SIMD size as these frameworks crashed for this size. For motion, we managed to evaluate 1 million parallel calls, but it required 10 gigabytes of memory for this, compared to SEEC's 700 megabyte earlier. And again, on the left side, SEEC performs worse for smaller circuits due to the triple batch size. And what this shows is that especially early deallocation and streaming of multiplication triplets are really good for these very large SIMD sizes where you want to compute on a lot of data in parallel but might be memory constrained. Okay, so now lastly, this last benchmark I promised, we look at the runtime of the ASCC benchmark with 100 chain circuits in our 3 network settings. In general, ABY performs really well runtime-wise for this circuit and tends to be a little bit faster than SEEC, except in the WAN setting. Interestingly, MP speeds have a very good runtime in the lowest latency network setting. For them, the runtime increases over proportional with the latency, and MP speeds is actually the slowest in the WAN setting with around 616 seconds, twice as much as SEEC. For motion, we see that it can't really make use of the low latency networks and has the highest runtime in the LAN settings. In general, SEEC has good online runtime performance in all network settings with room for improvement in the low latency network. Most importantly, using subcircuits, which we did in the ASCBC example, does not increase the number of communication rounds. Okay, so now to our summary. Now, SEEC, we achieve both a memory safe and memory efficient secure two-party computation framework. We provide a memory and communication round efficient implementation of subcircuits, which enable the use of functions in functionalities for secret sharing-based MPC. And I'm going to speed up a little bit. We also saw the benefit of our SIMD memory consumption, largely due to this early deallocation of data outputs and streaming of multiplication application truths, which can also be generalized to other protocols. And then on the right side, this is more a vague categorization by me on these frameworks on their performance predictability and their general reliability. In our benchmarks, we saw that ADY tends to have good performance predictability, and by that I mean that kind of performance-wise behaves as you would expect it, if it works, if it's not crashing, which unfortunately did happen, and we did also encounter memory unsafety issues in ADY. Then MP-speeds is a very good framework generally, but led to some confusing runtime results, but was quite reliable. Motion also very unpredictable, but quite reliable. SEEC, not as good performance predictability as ADY, I would say, but also very good reliability. Okay, thanks for your attention, and happy to answer any questions.